Completeness, what does it say here? Property of R. Okay, so can somebody tell me what's the most important thing here? The completeness property of R. Yes. Yes, Zara. So the most important thing is the set of real numbers. R has completeness property, but the set of rational numbers doesn't. We went over that, right? You remember a complicated thing we did? So now we're just going to do, so in other words, if you have a set of real numbers, if you have a subset of real numbers, that subset of real numbers will have a least upper bound or a so you need two conditions. You need to have a subset that's not empty. It's a subset of real numbers and not empty, and then there's an upper bound. If you have an upper bound and a non-empty subset of real numbers, then that subset of real numbers has a supremum, as in LUB, as in least upper bound. Okay, so let's do that. So that's what I'm writing here, because this definition is used in the proof for our theorem, the Archimedean property that we'll be looking at in a second. So the first line goes, every non-empty set of, as in subset, but the book says set, of real numbers, that's this guy here, that has, and now we're going to have the, so we have two properties about this subset of real numbers. It's non-empty, and the second property is that has an upper bound. Okay. So before we go to the next line, which will actually say something about supremum and LUB, let's draw. So here is our set. And then maybe, are we good? Okay, how about this one? Is this a pretty cool subset? This is a subset. This is a non-empty set, because look at that. To make sure it's really non-empty, we could also do, let's put 2 here and 3 here. Are we looking at a non-empty subset of real numbers right here? We could even call it, what do you want to call it? Sorry, keep going back to my home language. B. Yes, Sophia understands this secret. Now what? What's the other condition? Every non-empty set of real numbers that has an upper bound. We need an upper bound. Do we have an upper bound right now? We have an upper bound called 3, but it's actually, we could also put another here. Let's say 5 here. Is that an upper bound? We got now 2 upper bounds. And is 3 in the set B, Sophia? No. Emma says no fucking way. We're going to go with Emma on this. How about now? Is 3 a member of the set B? Yes. Alrighty then. What are these things called? Endpoints of the subset of real numbers. Just a quick, so we could just keep that. The next line says that if any subset like that looks like this, let's make this, that's just for the sake of it. Is 2 an element of B? No, not anymore, because it's not a square bracket. But so then it says the definition that has an upper bound, non-empty and has an upper bound. So I'm going to underline this. These are the two conditions. Then what we have is we have a problem with the blue. And that is also has an least upper bound, or also has a has a supremum in R. Yeah, so if this is true and this is true, in our case, we are saying, yes, there's an upper bound and there's another upper bound. So therefore, these two conditions have been met with this picture. If those two conditions have been met, then our axiom, this is a definition, tells us that then this set will also have a supremum. So does it have a supremum with this picture here? And Sophia says yes. And which one is it? Is it 5 or is it 3? Because yes, because both of these are upper bounds, right? Why is 3 an upper bound? Because no element of set B, all elements of set B are smaller or equal to 3. All elements of set B are smaller or equal to 5. So therefore, 5 and 3 are upper bounds to this set. This is the least upper bound because it is the smallest of the upper bounds. It's the leftmost. Therefore, yes. So this is our sup, as in supremum, or this is our LUB. And this is our just upper bound. We good? This is what we'll be using in our proof for the next thing. So I'm going to erase this. This for those who are taking notes. Okay. And yes, it is recording. Good. All right. How much time do we have? We have 30 minutes? Okay, we should be able to finish it, hopefully. Otherwise, it will be very sad. But I don't believe in myself, so yeah. I just believe in Jake and his arm. It's broken. I believe in broken things. I'm very sensitive. Yeah. Okay, let's do Bartle and Sherbert. Shouldn't have. And this is called Archimedean property. So the number is 243. Archimedean property. All right. Very exciting. What we're dealing with in this proof, and I haven't given you the statement, just the name of the theorem. The theorem says that, no, the theorem deals with natural numbers and real numbers. Okay, so here's the first formulation. And maybe, okay, the Archimedean property says, so let's write that. Archimedean property says, what does it say? It says that the set of natural numbers, is not bounded in R. Okay, so we just looked at that subset B. It was bounded in the real numbers. It had its upper bound was 3 and 5, and also millions on the right side. And here this statement. So what is this statement saying? It is saying that if you have a real number line, so I'm trying to draw a picture for this sentence that I just wrote. So here is my real number line. And it is saying that the set of natural numbers, which is a subset of this real number line, goes on forever after every little bit. So the set of natural n of natural numbers is not bounded in R. How should I show that? So between 1 and 2, there are zillions upon zillions. I'm doing a Carl Sagan, billions upon billions, uh, Brooklyn accent of real numbers. So what do we have here? The problem is it's kind of like we have to think about these natural numbers at intervals on the real number line. Okay, all right. So it is saying that what's the biggest natural number? 32? 30? Oh, on this, right? But in fact, it goes on forever, right? Okay, very good. 3, yes, that is true. Okay, now, yes, Zara. Archimedeans. It's the same spelling as this one. Archimedean. I know. I want to be a medical doctor. Yes, doctor writing. That's where I need to get to. Okay, now this is one way to express it. Now let's express it in a way that will, then we will do a proof by contradiction on that. So here is the definition of this theorem, and it goes, I think I'll just write it here, or actually I'll just delete this one. So please, if you got everything down, I'm moving here. And all righty then. So this says if x is a real number, how do I write that? X is a real number. I could say is a real number, or I could say if x is a real number, or x belongs to the set of real numbers, or x is in R, which is what this says, then there exists, this is exists, sorry, a number n, small n, a natural number, small n, how do I say it's a natural number? Belongs to, that's what I just said. I said, if give me a real number, and then I can trust me, believe me, that there will exist a real number n whose value, how big or small, depends on this x. How do we write that? We put it right here, little x. So this is a real number. This is a natural number. So the theorem is going, if you hand me a real number, I can prove to you that there exists a natural number n that depends on its value on this real number. It exists such that, and the condition is, what should be the condition that would tell us that there is no last n, that the n's go on forever? Okay, that could be very good. I like that. Or if I write x here and I want to write nx here, what should go here between these two guys? But that's actually nice too. There's probably somebody's done that. Very good. And also or equals. There's always a bigger natural number to the right, or the real number that we're looking at is one of those natural numbers, right? Is 2 a real number? Yes, it's also a natural number. All right, so let's try to visually see this representation, right? So we have the real number line, and somebody tells me, okay, we need to put in what? We need to put in our natural numbers in there, right? So we've been doing it like this. We're going to have 1, 2, ooh, I'm going to put this X here. Excuse me. I mean, I'll clean the room later. Okay. All right. Where do I put my N, X? So I have 1, 2. Let me put this guy here in. Oh, yeah. No, that's fine. Right. And the set of natural numbers keep going to the right. Therefore, if on the number line you give me a real number X, I can assure you to the right of it will be a natural number, or this real number itself will look like a natural number. Okay, so I'm going to put this guy, N is bigger right here, and so it's going to be in red here. Okay. All right. So I'm going to write this. I got pi here. If you give me the number pi, I can assure you to the right of the number pi is a natural number. Which one should we go for? Excellent. That's all. Give me another real number to the right of it will be another natural number. In other words, there's always a natural number going towards the right forever. Mr. Jake, you had a question? No? Okay. All right. All right. So that is the definition. Now let's do the proof. I mean, that's the, so you always need to take a time to understand the statement of the theorem, especially how the natural numbers are embedded in the real number. And that kind of sense, you need to have that in your head. Start with, we want to prove this thing here, right? This is saying that there's always a natural number to the right of any given real number. You could write this and go, there's always a natural number to the right of any given real number. And it might be itself, right? Okay, all right. Now, so we're going to do that. We're going to say that this assertion, so first thing I'm going to say is, or the book says, if, so this is our proof by contradiction. We're going to find something really stupid very soon. Proof by contradiction. This thing is not going to happen, right? We've got what, 5 minutes left? Oh, cool. Is there? We have 5 or we have 15? 20 minutes. Okay. Oh, shit. I could draw the whole world in 20 minutes right here. Is false. Any actual real math professor would just freak out the way I teach so slowly. So if the assertion, this one, is false, then how do we, what's the opposite of this? You drop the equal to's and you flip it. So it's going to be, we could do it like this. That's the opposite of this guy. Or this. This is better for us. For, oh, actually, they have an equal to. I need to check this. Might have messed up. Okay, I don't have time to check that. So I'm just going to do less than. Huh? Look, I take this class very seriously. See, the problem is my daughter and my wife doesn't have a sense of humor. So I have to express myself to my poor students, or add them or something in English. English is not my first language. Right? Isn't it the hardest, stupid language? Yeah. America, you need a new one. Yeah. I'm voting for Kamala because she's going to keep all the wars going. Yes. Okay. So is the English department. They're super excited about this war stuff. Okay, so here we have, what is this saying, folks? Very good. And now what is it saying for all n? Give me all the natural numbers, and I'll give you an x that is bigger than all these natural numbers. That's why they have this, because that's the definition of an upper bound. The definition of an upper bound is all the elements of a set are equal to or bigger than this upper bound. So this is the definition of upper bound. That's why they have the equal to sign there. Okay, for all n. So how do we show that? So let's do this. So I want to represent this false. This is a wrong thing, right? This assertion is completely wrong. How do we show that here? So we have an x. This is our real number. We have our set n. 1, 2, continue, 3, n. Which n is this? This is the largest, the last n. So we're going to call it Mr. Last. After this n, there are no natural numbers. Okay, so there might be, there might be, let's say, an x1 here. Is that true? There might be an x2, x15 here. Actually, there are billions of them. But there is one x where, yes. I know, it should be this. And I need to check the book, but I don't have time to make sure. Because the actual opposite of that is without the. So I think, oh no, we should keep it like that. That's right. So I must have copy pasted it wrong. No, because this is the last natural number, and this better be bigger than that. Otherwise, but the definition of upper bound is that it can be equal to it. Yeah. So we could check it right now, but we don't have time. Can you look it up? Okay. All right. Okay, let's keep going here. So that's a good point. All right, so let's go. So therefore, so if this is our assertion, this is the picture we get. What is this picture telling you, Zara? Oh, shit. Zara, you're Asian. Supposed to like math. Duncan, you're Asian. So, yeah, you look so Asian to me. Like South Asian. Doesn't he look like you? Because there are people who look like you in Afghanistan and some parts of India. So what we're saying here is 1, 2, 3, we are going to run into an upper bound. This n could be a very, very large natural number, but this is the last natural number. Okay, all right. So let's just make this cleaner. I'm going to make this because we'll be using this. So we got 1, 2, and sorry, another. Let's just keep them down here. So we got an n, and then this is our last n. Okay, all right. And I'm going to move this. So you might want to draw this picture here. I'm going to put my x right here. This is not going well. Here we go. All right. So if there is an upper bound, and this is where the axiom of completeness comes in, the completeness property of real numbers. Real numbers. We are applying real numbers to this. We are applying the completeness property of real numbers to this picture here. The picture tells us that we have a subset, the set of natural numbers. Is set of natural numbers a subset of real numbers? Yes, because it's contained in it. 2, Does it have an upper bound? What is it? X. Excellent. Very good. And so what was the, I know I should give her cash for this. What is the completeness property says that if you have a subset of natural numbers, of real numbers, which is the set of natural numbers, and it is not empty, right? 1, 2, 3, and it has an upper bound, then the property of completeness says it will have a supremum. I know, it's the moment. So there, actually, we haven't got to that line, sorry. Take the claps back. There is, if this is true, then we can say that there is, we're going to get to the supremum in a bit, is an X there, therefore, X is an upper bound. This X here, so is an upper bound of the set of natural numbers. So let's forget about all I said. Why is X an upper bound? Because it is bigger than any element of set of natural numbers. That's why X is an upper bound. Sophia. This is true and this is false. Oh. And we're drawing a picture that actually is a false picture of the world. Oh, okay. Yeah, okay. And then when we go with this picture, we're going to run into trouble. And when we run into the trouble, we say that our assertion, this idea that we should go with this is wrong. And the original, what this said is that there is always a bigger natural number than a given real number is always true. So, but we're assuming opposite. We're saying that there is a real number that is bigger than any natural number. And we're going to run into trouble right now. Now, because this gives us the upper bound, this is the definition of upper bound, a number that is bigger than any number in that set or equal to. Sorry, it's back. So now let's do the completeness. Now we're going to apply the completeness. If you have an upper bound and a non-empty set, then we can assert that this set of natural numbers that apparently ends on the last n here has a supremum. So I'm going to write that down there. And so there we have a second therefore, unfortunately. This is from the book. We're now applying the completeness. Who was that angry man? Shit, Sophia, come back. Your brother's still here. By completeness property, this book is trying to teach you guys through writing these sentences. The non-empty set N has a supremum, as in LUB, in, so it actually names it U. Does it? U. So it calls the supremum U, that is a real number. Okay, so what is X? It's an upper bound. If you have an upper bound and a non-empty set, then you have, according to the completeness property for real numbers, there's going to be an upper bound to the left of it, which will be the least upper bound for this set here. So we're going to stick it right here. And the book is calling it U. Try this again. Is this? That's a nice U. So which character is this? This is LUB or the sup, the supremum. Is everybody with me here? So now how many upper bounds do we see on this line? X, very good. And U, which one is the least upper bound? This guy here. We're applying because the key thing to remember is the completeness, a set of natural numbers does not have the completeness property. That's why we're only dealing with real numbers. That's why we get this guy right there. All right. Okay, so that's good. And this is when we do stuff to create the contradiction. If this picture is true, which it isn't, but we're pretending it is true, that the natural numbers kind of end right here, and after that, there's a least upper bound or supremum, a real number, and then all kinds of upper bounds, like x here, right? Okay, so now we go. So what do we have? How do we write this? Let's see. So we have u, and we're going to do an operation on u. U is what? It's a real number, and we're going to do this. We're going to subtract 1 from u. And if we do that, we get a number. And that number is called, gives us a, so if we subtract 1 from u, this gives us a number, u minus 1. Key thing today for the liberal arts folks, and for me last semester, this is a number. Everything on the blackboard is always a number, even if there are plus and minus signs around it. That's a number. So let's fit it. Where will it go? U minus 1. We took 1 away from u. Is it going to be here or to the left of u? To the left. Let's stick it. We could stick it even here. Doesn't really matter. I'm going to stick it right here to our n here. So u minus 1 is here. Okay, so let's now think about what's happened to us. We have a real, this is the least upper bound of the set of natural numbers. What the hell is u minus 1? It's a real number that is smaller than our least upper bound. That is not possible. This is the smallest real number that should, which we've decided. This is the smallest real number that we have decided that is to the right of all the n's. When we do this, we are now looking at a number that is smaller than the smallest real number we decided should be the upper bound. Therefore, we have a problem, right? So therefore, we have a situation that doesn't make sense. Is this an upper bound? No. And this is when the trouble happens. If this real number is not an upper bound, that means, remember, which means that there better be, if this is not an upper bound and this is the least upper bound, this is an upper bound, which means that there better be a natural number right here. Yes. Oh, why are you messing with me? Okay, so yes, that is true. So we have, and let's call that m. Since we have 5 minutes, I'm just going to go ahead and do that. So now we have a number m. Is that right? Yes, sir. Which is to the right of this real number, which shouldn't have happened because n was our last biggest natural number. And if that is, so that therefore we can write, so this situation that we have, u minus 1, and to the right of u minus 1 is an m. How do we write that down? We write, I'm going to write it up here. Yes. Yes, we've got trouble already, right? We have this situation now. We have a real number, u minus 1, which is smaller than m, which shouldn't even exist. So this condition here, I've written it out mathematically. And now the real trouble happens, because guess what u is supposed to be? U is our least upper bound, bigger than any natural number. This is a natural number. So if I add plus 1 here and plus 1 here, these two guys get canceled. And what we have here is u is smaller than a natural number m plus 1. which would be on this side here. What is this thing saying? It is contradicting. It's saying that there is a natural number bigger than our agreed least upper bound supremum. This is the contradiction. Therefore, this is a total disaster. Therefore, we're done. Okay. So yes, everybody understands this? Or the other thing is, nowadays people do this. How knows? After you prove something, you put a black square like that at the end. So back in the day, people used to write QED, I have proven the theorem. At the end of your proof for a theorem, you put a square, a solid square. This is from that famous mathematician.